Okay, good afternoon, everyone. So welcome to ECM 16 slash CSM 51A. So, well, let's see. Yeah. So, by way of introduction, my name is Manish Srivastava. So, for this quarter, we are going to navigate through digital logic together. By way of some background, I'm a faculty in both ECE and CS department. My group works in an area called embedded computing system, essentially computers which are embedded in physical systems. They interact with the real world with sensors and attempt to manipulate the physical world. And we worry about things like how to make them efficient, how to make them intelligent, how to deal with security, privacy, these kind of issues. We are located in Bolter Hall. Were you to be there in person, you would probably pass by my lab every day because we are right opposite the main elevator. In any event, that's me. The course staff also includes two TAs. One is Akash Deep Singh, who actually is my PhD student. So he works on some of the things naturally that I do. In particular, he's doing some pretty cool stuff on how you can identify hidden sensors in spaces around you, dealing with security, privacy issues. And in order to do it, he applies methods from AI and machine learning in that. Our other TA is Star, or Saida Lee, goes by the name of Star. He is in, he's also in ECE, works on circuits for biomedical devices. He's a very experienced TA, so you're in good hands. For Akash, it's the first time around TAing, so I think it's going to be a learning experience for him as well. But anyway, so we have two excellent sort of students who are part of the instructional staff, and they're going to help you out. Okay, so that's a little bit about us. Also, before kind of moving on, I wanted to talk a little bit about how I would ideally like these lectures to be in. So in a physical class, of course, we can look at your faces easily and kind of interact. I would like to replicate that. So I would really encourage you to interrupt me along the way. If you have any questions, just feel free to just chime in, like I have a question or something, right? I mean, unfortunately, it's hard to kind of keep tab on what is happening on the chat. So if you don't see me responding, just speak up. That way the class is interactive. That way you also actually slow me down and explain things again. So that's very useful. Of course, we'll be recording all the lectures, and I'll be putting them up on YouTube as well as CCLE. CCLE, obviously, the YouTube link is going to be on Piazza after today's lecture. So anyway, so you'll have multiple ways of doing this stuff. Okay, so our schedule, I guess if you downloaded the slide a little bit earlier, Akash pointed out that I had listed lecture hours as 4 to 6:50. That was obviously wrong. So these are 1 hour, 50-minute lectures. We have 3 discussion sections. And as of a couple of hours ago, everyone who was on the waiting list is part of is enrolled in the class, so you should all be in. I've also listed the office hours out here, but basically every day of the week you will have someone available. And also I'm holding my office hours in the evening because I realized that some of the students are not in the country, so kind of trying to find times that can work sort of more conveniently for everyone involved. So anyway, I think we are going to be available by a variety of means: office hours on Zoom, and by the way, there are 3 different Zoom links. Okay, I don't have them here, but they're on Piazza. One for me, one for Akash, and one for Star. And so yeah, plenty of interaction. I was just curious on how the class composition looks like. It's obviously a course which is required for everyone in ECE and CS department. Roughly half the class is ECE. Roughly 40% of the class is one of the 2 CS degrees, CS and CSE, and then a little bit from our nascent computer engineering degree, which is run by both the departments, and then a few physicists and other engineering. So good mix of students. Particularly, we have people who, I guess, love hardware. That's the ECE side, and those on the CS side. Hopefully, you don't think hard. My goal is to convince you that without that, hardware is cool also. Okay, so hopefully we'll get to have that. For many of you, you're probably freshmen, so it's one of your first or one of the very first proper engineering class. So I'm sort of aware of that. M16 kind of sits right at the beginning. So what is this course about? So it's titled Logic Design of Digital Systems. There are a whole bunch of okay, so let me just take a moment to answer. Can you attend any discussion section? Ideally, no. And the reason simply is that there are rules that govern how many students a TA can manage. These are because of the TA union. So I cannot consciously permit. Now, occasional part is fine, but I don't want a grossly imbalanced discussion section. So unfortunately, the answer to that is no. We really want you to stick with the discussion sections you are in. Occasional exceptions are fine, but we do have a hard limit of 30 students per class according to the rules that govern the TA. So hopefully that answers it. Is there a group me for this class? I have no idea what group me is, so I don't know. Let's see, someone else. I know in the past students have run Discord forums for this class. You're welcome to do it. We use Piazza as a forum, so that's where the official presence is going to be. Anything else that you do, you're on your own. Okay, so discussion, back to this logic design of digital systems. So I'm going to spend a moment trying to tell you what this is really about. So one part of this thing is digital systems. What does I'm sure you have all heard the word digital systems. What do you think digital systems are? Anyone?
Like one where the input is discrete, like a 1 or a 0.
Yeah. So input is discrete. Is right on. There is actually another thing which is very common to digital systems is that they are also discrete in time, in the sense that they change values at discrete moments in time as opposed to continuously changing. So you could so later on in the course we'll see that, but you're right on. So digital systems, the word digital comes from digits, fingers, right? So discrete value doesn't have to be binary, so it doesn't have to be 0, 1, but it's the most common one. So what's a system? Well, system is something, at least for purposes of most of engineering, something that takes some input, some information input, and produces some information as output. Right, so that's a generic definition of system. A digital system is a system where the inputs and outputs are digital, and also the processing is digital, right? How you manipulate that information, how you manipulate the input to produce the output, that too is done digitally. And digital form is like basically it's discrete, takes a bunch of finite set of values. So like we encounter it all along. I gave the example of fingers, gears in a car. Yes, there are cars which are continuous gears, right? Some of the Hondas are like that, but most cars have discrete gear settings, for example, right? So that's a digital. What's not a digital form? Well, most of the world is continuous, right? Or at least once you are at a sufficiently macro level, right? Deep down, the world is digital, right? Quantum states. But once you move up, all our physics and all tends to be continuous, right? We think in terms of length, height, voltages, chemical concentrations, all these kind of things. We really think of them as continuous values, right? So much of the world is, so it's kind of interesting, right? Really deep down, things are particles and quantized, but then at most of our real world experiences are continuous, and then we layer a discrete sort of abstraction on top of this otherwise continuous world. So let's look at some sort of examples. Sound waves, right? Sound waves hit. So if you think of like a microphone, so what happens is sound waves hit a diaphragm in the microphone, and then that diaphragm vibrates, and that diaphragm is attached to some sort of a circuit, so kind of which you see out here. And what happens? Some resistor, capacitor, inductor, things like that. The point is that as the wave hits this diaphragm, the diaphragm vibrates, the electrical characteristics of the circuit changes, and therefore some electrical value changes, right? Usually the voltage, could be the current, could be capacitor, could be resistance. So this is analog, right? Changing continuously here. Let's look at our digital assistant type devices. Now things get sort of more interesting, right? These are usually some hybrids. So if you look at, in this case, the Amazon Echo, so they have microphones which listen to your sound, and then that gets digitized, and then that digitized waveform, the digitized sound wave, is we then do things like speech recognition on it. After that, some natural language understanding to kind of make sense of what the person was asking, and then it consults some appropriate application and then responds accordingly. These devices are actually pretty cool. One of the things I'm sure you may have heard about them is how they have arrays of microphones, right? Instead of a single microphone, they have multiple microphones. Why do you think they have that? So, anyone?
Could it be for error catching?
Error catching, no. Could it be determine which direction the sound?
Yeah, which direction? Excellent. Yeah, indeed, which direction. So what happens is the following. How do our ears work, right? We have a sense of direction, right? And the reason is when the sound wave hits the two ears, there is a tiny difference in intensity, but more crucially, timing. And our brain processes it, and so we can hear about the direction from which the sound is coming. These devices do exactly the same thing, right? Of course, they tend to have more than two microphones. Usually, if you open them up, you will see like 4 or 5 or even 8 microphones. And in case of Amazon, these devices, they are only looking for the angle of arrival in the XY plane, in the horizontal plane, but more sophisticated one can give you direction in 3D, right? So they will have the microphones in a tetrahedron or some such shape. Okay, and so what goes on behind is they measure, they look at they compare the sound at the different microphone, and look at like slight differences in time of arrival, like when the sound, when the feature of the sound of the different microphones, and then processes it using a type of algorithm called beamforming. And the idea is at the end, it kind of gives you which direction the sound wave is coming from. Okay. And then you can have 2 or 3 of such things. and then you can have directions from each one of them, and you intersect it, and you can even locate precisely where the sound source was. So pretty cool stuff can be done, and this is where you have kind of hardware, software, algorithms, all sort of coming together to do this stuff. Okay. Now, I mentioned that most of the world is analog, right? I mean, all these different signals that we encounter, sound waves, voltages, things like that, they're all analog. And yet, much of this processing that we talked about is taking place through computers, either built into these devices or up in some data center. So how do we go from what is an analog signal to something which is discretized and processed? And that job is done by specialized circuits called analog to digital converter and digital to analog converter, pretty obvious names. So essentially, as the name implies, they take continuous valued things which are in continuous time, they digitize them, and now they send out a series of numbers or series of discrete values. And the D2A converter does exactly the opposite. It takes a series of discrete values, and we'll talk about how to represent them, and then generates back these kind of waveforms. Maybe it could be pressure, or like that's what a speaker does, right? We send bits. D2A converter converts it into some voltage waveform. That voltage waveform then moves the diaphragm on the speaker, and that diaphragm then moves the sound, the air pressure, and that's what falls onto our ears. So we have all these examples of like going back and forth fluidly, and design of these things is pretty complex, pretty challenging, but you need to get it right, because if you don't do this correctly, then of course everything else falls apart. So there are several people in the ECE department who kind of focus on creating these things. Okay, in some cases they have to be really, really very subtle. I mean, like circuits which measure seismic waves for detecting earthquakes, things like that. They have to be super precise. So often, like commonly, you will see that the digital part may be like somewhere like 8 to 12 bits, but for very sensitive applications, it might be like 20 bits or 18 bits. Okay, so a lot of work gets done on there. Digital systems abound as well, right? I mean, we grow up with this, calculators and whatever, home automation stuff, and our vehicles and things like that. So there is kind of just no shortage. I mean, computers are everywhere. So when I talked about my own research, I said we work on embedded computing, right? So computers which are inside other objects, right? As opposed to your laptop, desktops and all. So embedded computing embedded in other stuff, and increasingly that other stuff could be us. So Star, our TA, right, he's from a group which does stuff where these things are implanted in your brain or other parts of the body, sensing and sort of doing stuff inside the body. So some pretty cool stuff happening on sort of things which are embedded. So just want to present some examples. So a couple of years ago, Tesla obviously has been making a lot of news about like autopilot, self-driving, fully autopilot, things like that. A couple of years ago, they kind of released a chip of their own design for this purpose. So just want to show that example. So in this case, this is a circuit board, kind of the big thing that you are seeing, and the two highlighted stuff are the two copies of their chip, and this thing processes signals coming from radar that the cars have, GPS, so that's the satellite signals to get location. There is map information. There is IMU, which stands for inertial measurement unit. So apologies, my pen is acting up today. So this thing stands for inertial measurement unit, And what it does is it measures acceleration and sort of angular velocity and acceleration and magnetic field. Okay, so it basically gives you what forces are being applied on the car and where is it relative to Earth's magnetic field and things like that. Ultrasonic, so these are sensors which spit out ultrasound and then look at the return signal. They kind of act as same purpose as radar, except in the sound domain. Wheel ticks, how rapidly the wheels are moving, steering angle, and of course, I forgot out here, but there's also cameras, right? So all of that is being processed. Traditionally, for something like this, you might use GPUs, which are on your like NVIDIA's GPUs, for example. But for a lot of these applications, this processing is being done by more specialized computers, and this is kind of an example of that. Okay, so this Tesla chip is actually, the reason I kind of mentioned that is because it's actually a pretty amazing device. If you kind of peek inside it, it has graphic processing, much like the NVIDIA GPUs that you find. They're used for Bitcoin mining and video gaming and whatnot. So they have that. They have circuits in them which are specialized to process what are called as tensors. Tensors are like general form of matrices. So essentially, these are specialized computers that can handle large matrices. That's one way of thinking about it. They also have these things called neural processing unit. So this is for doing computation associated with neural networks. And then, of course, there is a regular computer, which is referred to as just a central processing unit, right? This is kind of like orchestrates everything. So all of that goes on in one chip, and each chip is like billions of transistors, right? I mean, there's a lot of cool stuff kind of going on in there. Consumes lots of power. Probably this chip must be around 100, 200 watt type power. So consumes a lot of power. And of course, nowhere near our brains still. Okay, I mean, these are very sophisticated, but still far off from what biology does. These Tesla chips are some of the largest chips that have been made. I mean, Intel processors that you find in servers and all are pretty big. So are these Tesla chips. NVIDIA GPUs are also another example of a really big chip. If you, this slide shows RTX 2080 Ti, right? That is, I guess, no longer the most recent GPUs. 3090 is the current one, if you can buy them, because they're very hard to find, but those are the latest NVIDIA GPUs. So there's a race going on, right? I mean, Intel makes the CPUs, and companies like Tesla need CPU and AI machine learning, and companies like NVIDIA are into the business of doing video gaming and Bitcoin mining, and of course AI, and so a lot of cool stuff going on. Okay, so that's one end, big stuff, big computing. The other end is tiny computing. So your Apple Watch, which I'm sure some of you have, that represents the other end. So performance obviously matters, and there's a lot of intelligence in these things, but also what really, really matters in this case is something else. Anyone? Like here, we care about the performance. What do you think we care about here?
Power consumption.
Power consumption, yeah. Power consumption and size, right? These two things. Power consumption, absolutely, right? I mean, they're pretty far off. So computers which are designed for this tiny end, right? We want intelligence, right? I mean, we are doing handwriting, and of course, a lot of these devices have sensors and recognition and all going on. So they also have AI, machine learning type stuff going on, and a lot of processing. But of course, the size and energy, and of course, cost, right? I mean, no one will buy a $3,000 watch, or most people won't, right? So they're operating in a different kind of regime, and of course, just look at how densely packed stuff is. I mean, it's kind of a marvel of engineering in many ways. So if you kind of dive inside, you will see that actually it's not a single processor, a whole bunch of chips there, right? There's kind of the main processor. power management ICs. There is, of course, the chips that communicate with Wi-Fi, and also in the newer versions with the cellular radio, right? So you see all of that. There is also like management of charging and all. There's a whole bunch of stuff going on, okay? And if you kind of look at these things, the computation part is just one aspect of this whole thing, right? So that's this Apple application processor, right? That's the it's a big chip that you see in the middle, but it's you have an equally big amount of memory, right? These watches have now what like mine has 8 gig, right? So it's pretty amazing what they're able to pack in this thing. Okay, so the third example is a more recent one. I'm sure many of you probably watched that pretty cool landing of the Mars rover just a few weeks ago, and kind of the helicopter it is carrying, a drone, right? I wanted to cite this one because it's an interesting example. So what's the brain behind that rover, right? So this rover has 2 identical compute elements, okay? One of which is normally asleep. By the way, we also saw 2 in the Tesla case also. Why do you think they have 2? Why not just 1?
I know parallel computing is a thing, but it'd probably be a lot faster if you had the 2.
Yeah, that's true. Although if you notice out here, it says one of which is normally asleep, right? I mean, so we are actually not even using it. Right? So you're absolutely right. In some cases, you have to, yeah. So go ahead. Someone else?
I was going to say it could be if one of the chips happens. If one of the chips happens to like break down.
It's basic. Actually, I think your voice is cutting off towards the end, so I'm missing what you're trying to say.
It could be like for consistency reasons. If like one of the chips, or if like one of the chips like is damaged or something, the car will still work, or the rover will still work.
Yeah. So you're right. So there are usually 2 reasons why we put multiple copies. One is in applications where you cannot afford failure, okay? And in which case you are going to put multiple, except that you're going to put at least 3, right? I mean, the idea is then they will all be running and they will be computing in parallel, and you're going to compute the result, compare the results, and then go with the majority. So like space shuttle or these rockets and all often have these redundancy, as it's called, right? Multiple computers independently running, producing, let's say, when to fire the engine or stuff like that, and then deciding. In fact, the whole Boeing fiasco that happened, Boeing Max 800, right? I mean, it was because they didn't, for the very critical piece, which was the sensor in the nose of the planes to measure the airspeed, they didn't have any redundancy. It was a pretty, I guess, bad engineering design. So that's one. And by the way, a lot of work in that area happened right here at UCLA in the 1960s and 70s in the CS department. But there is another reason, which is where repair is going to be impossible, right? Rover is a great example. You can't just go to Mars and replace the bad chip. So that's the only reason that they have out here, which is 2 of these. In case of Tesla, both of them are active, and they kind of do the parallel processing part, which sort of one of you were mentioning earlier. So in this particular case, these compute elements, then they talk to sensors and all, right? I mean, to memory, and you notice inertial measurement unit is again out here also. It's a very powerful, cool sensor, which by the way is also an Apple Watch. All 3 of my examples have these IMUs, okay? These computers monitor the system's own health, as well as obviously controlling the science instruments that this rover is carrying. A very interesting thing out here though, the processor being used out here is this device called PowerPC 750. Okay. Guess how old it is? It is the same processor, or essentially the same processor, which was used in the original iMac. I suspect most of you were not even born. then, okay, in 1998. So what's going on, right? I mean, why is NASA? I mean, remember, why is NASA using this such an old stuff? Okay, any ideas? I mean, they certainly have no shortage of money. This rover is, I think, $2.7 billion.
I think if I remember correctly, it's because they wanted a chip that had proven reliability for an extremely long time.
Excellent. That's absolutely one point, because everything has bugs. These chips are so complex, and then the software which runs on them adds another layer of complexity. So they have worked out a whole whatever compilers and operating system and application software, and of course the hardware, all these things, like we know where the bugs are and all. So absolutely, that's one of the points. Anything else? So actually, the thing that I didn't mention is this radiation hardened, right? That's extremely critical. In space, you are being bombarded by radiation from, well, from the cosmos, rest of the cosmos. Much of it is stopped by the atmosphere. So once in a while, even on Earth, you have memory errors and all happen because of these particles which are coming in from outside space. And so that is why you have memory which have error correcting bits, or CPUs which may have some extra parity bits and all. But it's a much bigger deal in space. So these chips are designed to be radiation hardened and all, and that takes a lot of design effort and all, right? I mean, we have to kind of essentially re-implement these things. So as a result, this PowerPC 750 chip is around $200K, the one which NASA is using. Okay, so it's not your $500 Intel chip, even though the Intel chip is a lot more transistors and a lot faster. And the reason is this kind of that hard part. Okay, so it costs upward of $200K as a result. So with these three examples, I wanted to kind of show you that the richness that exists, like were you to get into computing systems, whether you are a CS person or an EC person, all these different points in this in our design space, right? I mean, like autonomous vehicles on Earth, autonomous things on other planets, and these tiny little stuff on your body, inside your body, and there's a whole bunch of other cool stuff. Okay, and I think that's what sort of keeps at least me personally interested, and a lot of us who do research in this space. There is a lot of cool stuff happening around there. Okay, so that's digital systems. I guess the point wanted to make was that digital systems are kind of pretty cool, in my opinion. Okay, so the other part is, what do we mean by logic design of digital systems? So what this really boils down to is, in how do we make complex digital systems from simpler primitives? Engineering is fundamentally one of the key things. One of the ways engineers handle complexity is by breaking things into simpler stuff, right? In digital systems, we call those simpler things to be logic gates and state machines. These are kind of the two building bricks of digital systems. So we're going to spend a lot of time looking at these. And kind of the idea then is that when you write software, you take an algorithm and you map it to Python or C or Java, whatever programming language you are doing. When we design digital systems more generally, then we again take our algorithm and now we map it into hardware, or hardware plus software, or hardware may be given to you and you are just doing the software. Okay, so kind of if you step back, what people who do digital systems, they could fall into one of these three categories. One is like, it's so power constrained or so high performance that everything is going to be just hardwired. My algorithm will just map into hardware and I can't afford the luxury of software. Then other extreme is, I really don't care about the hardware and all. I'm going to take off-the-shelf hardware like an Intel processor or something like that, and then just focus on software and map my algorithm into software running on that, right? And then in the middle, which is the more common case, and all the examples I cited fall into that category, where you do this, you take your algorithm and you are designing both the hardware and the software. It's something called as hardware software co-design. So some of your algorithm may go into hardware, some will go into software. And one of the things I hope that sort of you take away out here is that we are all working at the level of algorithms and mapping them into this set of hardware and software, right? I mean, what if you whether you end up being an app person or whether you end up being a hardware person, at the end of the day, you work with algorithms. And in fact, how we design these digital systems is often that you write your algorithm in some programming language. Either it would be something like Python or C or Java, or there are equivalent languages which focus on hardware. So they're called as hardware design languages, Verilog, VHDL, there are other stuff like that. And then oftentimes there is a middle. I write my algorithm and then I let some software tool figure out which part goes into hardware, which part goes into software. So that's how we kind of design these things, and we'll examine some of them through the course. The other thing is really, this course is not intended to be just to teach you tools. In fact, we do that, but that's not the main part. It's really first principle understanding of how these systems are. And actually, a very nice interview I was reading of Elon Musk, where he kind of emphasizes that how critically important when you are solving a problem to decompose it back into its first principles and then go back up and sort of come up with the solution. It's very easy to fall into the trap where you kind of learn how to use a tool, PyTorch, TensorFlow, some favorite tool, and then faced with a problem, you just apply the tool. The problem with that approach is that if things don't work, you don't know why they are not working. And if things fail, let's say your system crashes, now you're kind of left clueless. More importantly, over time, technology changes, applications change. So very important as you go through your curriculum here at UCLA is to become familiar with the foundational concepts. Skills can be learned anytime in your life, and you will learn them again and again because they'll keep changing. Foundational stuff doesn't. So part of my goal is to really give you a good understanding of that. Third one, you don't want to be just building systems. You want to be building good systems, okay? And like anything, right? Whether you are a civil engineer or computer engineer or electrical engineer, that good part matters, right? We want to design systems which are efficient, which are consume low power, will cost low, will be robust, and all those kind of things. So we'll see some of those issues. What will we not do in this course? We will not worry about how those logic gates are built using transistors or other means. That's something that courses in ECE cover on the hardware side. We will also not worry about how we implement and manufacture these digital systems. Again, the courses in ECE cover that. And likewise, we'll not focus on software that runs on these digital systems. And I would also add software that designs these digital systems that, again, people in ECE and people in CS sort of do a lot of. So the scope really is in kind of this middle thing. We take the software for granted and we take these transistors for granted and we kind of focus in the middle. So that's what we'll be doing. So our building blocks, as I mentioned earlier, are these two things: logic gates and state machines. And these are generic concepts. They are applicable to both hardware and software, although more commonly people associate them with hardware for sure. But they are also used, for example, when you're designing a user interface, when you are writing instructions for a robot, things like that. Okay, so the real difference is how do you implement it, right? Remember earlier on I said I can map things to hardware or map things to software or map things to a combination of the two. I guess in this course, our bias is more towards the former, mapping things to hardware. But the way we think about our digital system in terms of these gates and state machines, that's generic. Okay, so what you see in this figure out here is how people who design user interfaces often think about, right? So each one of these circles that you see is kind of like a state where the user interface currently is, like a welcome screen and then a home screen, and then you move between, you can literally think of them as like the display or that you are seeing, and you move between them based upon user action, right? If I press the left button or if I select a menu entry or do something else on the interface, I kind of move to these different screens or different information gets displayed. Very much like this, we will see later on we use for digital systems. In fact, the concept of state machine is general. There is nothing which says it's about hardware or software. Both sides use it. The trick is there when you map, whether you map it to hardware or software, and that presents different considerations. Generally speaking, hardware is faster to run. Hardware is more difficult to design. Software is slower, lower performing, but it's easier to design. Now, again, this is a very hand-wavy kind of argument. It's often not the case. Also, software has its own advantages and hardware has its own advantages. So what we are seeking to do is to design good digital systems, right? As I mentioned several times, that we can take the specification of a digital system and we can map it into hardware alone, we can map it to software alone, or we can map it into a combination. And the two have their own pluses and minuses. Software is more forgiving in design. If you make a mistake, you can rapidly revisit, right? You just fix the bug, rerun the thing, and voila, you're good to go. So cost of iteration is low, right? That's the so design cycle is more rapid, and which is why it's barrier to entry, is easier. That's why you have more people doing apps as opposed to people who are designing chips. One is just harder, costlier in a way, right? There are other reasons also, but that's one. Which is why, faced with designing a digital system, if you can do it in software, then that's a preferred way to do it, because you will do it quicker. Hardware requires more principled design, right? Because cost of iteration is very high. So like every time you make a chip, right? That chip may cost if it's a low-end chip, maybe it would be like $25,000. But it's a high-end chip, like what Intel is doing and all, it would be a couple of $100 million. And if you now make a mistake and each iteration is costing you tens of millions of dollars, you are going to be more principled about the design, which means you're going to test before fabricating. Another place where is if cost of failure is high, right? In case of NASA, they're sending this rover out there. If there was a bug which went missing, then boy, the rover is on Mars. Too late to fix anything. And NASA's missions in the past have suffered from bugs, including kind of the Pathfinder mission in 1990s, where there was a software bug which caused their rover to repeatedly crash out in Mars. And fortunately, they were able to fix it remotely, but they were lucky. Tesla's example. If there is a bug, your car will crash. And plenty of examples have happened where because of software issue, these autonomous vehicles misbehave. There was a famous example from Tesla from maybe 5-6 years ago, where this car, which was going on the road, the driver was busy playing some video game or something in the car. But point was, there was a big rig along the road laterally. And the car thought that the vision system of the car thought it was actually a road sign, right? You know how we have those highway signs which kind of straddle the highway. So the car thought it could go under it because it thought it was a road sign. And of course, it was a pretty tragic accident because kind of the car just got sliced off. You want to detect these kind of problems beforehand, right? So principal design in many settings is very important. On the other hand, if you're designing an app for iPhone, which will whatever help you get grocery, I mean the cost of mistake is a lot more tolerable. So where does that leave us? Well, in order to design systems in a manner which is principled, there are some good practices that over time people have learned and which are equally applicable out here. So first thing is, you really want to systematically represent the design, right? What you want out of the design, what should the system do? As well as systematic ways where you can take this specification of what your system should do into its implementation, right? So that's the part out here. How to translate concept to physical system, how to translate the algorithm we have in mind to a logic design, right? All these steps. So a lot of time we'll spend on that. Another thing which works very well in engineering is modularity. The idea which I talked about earlier, also breaking things into simpler stuff, right? So if I get the simpler stuff done correctly, then I can just focus on putting them together. I don't have to worry about the whole thing. So like when you are designing software, you kind of assume that Intel did its job correctly and the processor does what it says. Hierarchy is the third one, which is kind of closely connected. The idea is that I think of the system in subsystems, and then I break the subsystem into even smaller subsystems and so on and so forth. So hierarchy and modularity often go hand in hand. Partitioning. This is kind of a concept which is very unique to digital systems, but kind of the idea is that anytime we think of an algorithm, there are two kinds of operations that go on. Those which are like arithmetic, right? Addition of numbers, subtraction of numbers, right? Sine, cosine, like processing of the data. And then you have things which are controlling the logic of your algorithm, like if then else or for loop or things like that, which are changing the direction in which the algorithm is proceeding. And it turns out it's very important to separate these two things out in order to get a clean design, and we'll see that later. Then comes minimization and optimization. Optimization is really, really key to any engineering, which is really, for the same requirement, I may have a car which is expensive, fast, but big. Or I can make a car which is slower, more efficient, and smaller, right? I mean, I can take the specification of commuting and really kind of map it into many different things. So always we have some goal, right? Optimize. What am I optimizing for? Am I optimizing for power or speed or whatnot? And so all those considerations come in. And this is like really big business. There are companies which design software tools which can help optimize your digital systems. And a couple of examples of these kind of companies, for example, is a company called Synopsys, which is kind of you never hear about them. Synopsys. They basically create software which companies that design digital systems use in order to optimize their design. Okay, so companies like Qualcomm or Apple or Intel, they kind of are customers of companies like Synopsys. These are software tools which are super expensive, like a single license of Synopsys will probably be $250,000 or something like that. So these are not ordinary pieces of software because so much is riding on them, right? I mean, they go into designing hardware which is multiple tens of millions of dollars. Then you have ways to improve the speed or improve power. Parallelism, which we discussed earlier, right? Tesla had two of them, two processors. Pipelining is another concept, which we'll do very late in the course. We have to worry about how different parts of our digital system talk to each other. And then I already mentioned these tools that help you design, right? all of these things kind of go into digital systems. We'll cover most of these, but with different levels of depth as we kind of go along. Just right now, I mean, of course, you haven't seen any of this stuff, so it may be overwhelming. But at the end of the course, I promise you, you'll find that a lot of these things that sort of we're emphasizing, and hopefully a lot of these lessons would be things that will not just be about digital systems. They are equally applicable, as I said, to software or systems of any type. So that's the goal for the course. Now let's talk a little bit about some of the logistics. So we have a textbook, Daly and Harting. It's a pretty old book, September 2012, as you can see. There is another version of it which says Digital Design, a Systems Approach Using VHDL. You can pick that one also, it doesn't really matter. And frankly, it seems there are sufficient PDFs floating around on the internet that whatever comes your way is fine with me. You can just decide. It's the version which says based on VHDL is available on Kindle, as in it's available in digital form. Whereas this one, which uses another language called Verilog. Verilog and VHDL are two languages which hardware designers use. This one is only in a hard copy form. My lecture notes should suffice. So honestly, I don't think you need to buy the book necessarily, other than for the problems. Basically, the material itself, I think the lectures, the slides cover pretty extensively. This book has remained in first edition, so there are typos and errors. So one just got to be careful, but again, sort of wherever there's a conflict, lectures override. Okay, so I think we'll take a little pause and then just see what questions. Okay, so someone created Discord. Why this textbook did not speak about the number system? Okay, the question, well, I can't speak for the authors, but no book is complete. Honestly, these are broad areas, and every book is a matter of trade-off. This book didn't go into number systems that extensively. Some other books do. There is also a course here at UCLA at the grad level, which is on computer arithmetic, and it goes very extensively. So it's a bit more of a specialized topic. So many books don't cover it that much. Okay, let's see. So that's the book. Any questions? The book has many chapters. We are not going to cover most of them, many of them. So let me just walk you through. There is another interactive book at Circuitverse, which I also found to be pretty good. It has a very different style, but you might find it more accessible. I think at some level, almost any book for digital system, they're like 80-90% overlapping. So which the problem that happens is that the jargon differs, right? I mean, they may use different symbols and things like that, but as long as you're willing to look past them, many of these books can do the trick. Online presence, there is CCLE. I will upload the videos on CCLE, mostly because university requires that the videos be posted out there, particularly for accessibility reasons. But I will also be posting the videos on YouTube, which many students find more convenient. I leave it up to you to decide. Usually the YouTube video comes online quicker, much quicker than CCLE. But that's a trade-off. All other material would be on Piazza, and it would actually, other than the solutions themselves, it will actually be all public. So if you don't want to sign up for Piazza for whatever reason, you can still access the material, but you will miss out on the Q&A. But you'll have to live with just office hours in that case. So Piazza, we have talked about, basically putting links to everything there, and you should already be signed up, because unless you enrolled in the class just recently, or your email of record on registrar's Office is not the one which you normally use. So access code I had sent via CCLE, so you should have access to it. If you didn't receive that email for whatever reason, just contact me. Okay, email is generally not a good medium to contact us in terms of response time. I would say limit the email only for truly very personal stuff, right? Something which you are uncomfortable putting anywhere else. Although in that case, I would also urge you should make sure you are sending the email using your UCLA account, right? In any event, if you're sending an email, put the course number on it so that I have filters which kind of highlight them. Otherwise, it's quite possible spam filter may not deliver it to me. We'll use Gradescope for all submission and grading. You should log in using your UCLA credentials, because again, what I've done is in Gradescope, we sync with the registrar record, so it pulls things there. I had synced once a couple of weeks ago or so, I think, and I'll do it again just so that it remains up to date. So when you go to the Gradescope page, you would see two login options, using your email and all, or using school credentials. Do it using school credentials so that it appears. Or alternatively, I think Gradescope allows you to link your school credentials with your regular account. You can do that as well. But okay, and then we'll be making heavy use of Gradescope's AutoGrader. So some of you may have done software courses where they grade your assignments by testing it against some test inputs. We do the same thing for all the design assignments. And also for quizzes, we will be using the AutoGrader, and even for some of the regular homeworks where I will require you to put your answers in a very structured format so that again we can auto-grade them. For classes of this big size, I like to have consistent grading, so auto-grading kind of helps me with that. Okay, one thing which I would really emphasize is the importance of, please do read the instructions, because we do ask for submission in very specific formats, file names, what goes inside the file. They should follow some structure, because if you don't follow that structure, then the AutoGrader will give you 0 score. And if we have to manually grade, my policy is simple. We are going to deduct 20% as penalty for not following the instructions. Okay, so very, very important that you follow the instructions that are written. Okay, so let's see, any further questions? Will we have a break during the lecture? We will at the halfway point. Let's see what else. How do we get the class code? Let's see, I had sent it on CCLA, so you should have received it. Akash, maybe could you just put in the access code onto this chat so that everyone has it? So access code for Piazza.
Done.
Okay, grading schema. So we'll do that and then take the break. Okay, so we'll have problem sets accounting for roughly a quarter of the course. These will be conceptual problems, may require the use of software tools. Likely 2 problem sets, possibly 3. Okay, unequal weight. Design assignments. This is, to me, the core of the course. I mean, digital systems really is an exercise in design. So we'll have 3, in all likelihood, maybe 4, but again 3 design assignments. These will definitely be software tool based and will be exclusively, the design component would be auto-graded, and the written report is something that we read. For the problem set, it will be again a mix of auto-grading and manual grading. Quizzes. We'll have 2, maybe 3 quizzes, 15% point. These are online, as in on Gradescope, with a designated start time and time limit. They're synchronous, so as in everyone does it at the same time, and time enforced. I will have 1 alternate time slot. So at least last time, I had some students who were in very inconvenient time zones in India and China and all. So I'm doing a second alternate time slot, which will be either late in the evening. So like the primary quiz would be during lecture hours, but one thing would be late in the evening, or early following morning. There. I know there are a couple of you who the university has granted special accommodation. Please reach out to me because I have to discuss quiz arrangements with you because you will have to conduct that in some special manner for you. The exam would be a take-home final, and it will actually be mostly design focused. Again, the design component would be auto-graded. There will be a bunch of questions around your design, but and one thing that I allow the students to do is that if they so wish, like if they made some unusual choices, or if your design is partially working and is not going otherwise, if you want, you can give a separate explanation via a video where you can show partial working of your design or whatever you like through screen capture or when things are running on the tool and all. So some students find it useful to do, but you only need to do it if you are struggling with getting the whole design working. So then participation 3%. And this would be through Q&A in the discussion, during the lectures, participation on Piazza. One of the things we'll be doing is we'll often have these very simple Q&A during discussion section, or it will be like super time limited, like you'll have 1 minute to answer or something. Okay, that's our way of seeing that you are actually participating and engaged, and just generally how you interact on Piazza. Answer meaningfully. So I filter away random mails and all. And one other thing I would say on Piazza, you can post anonymously to your fellow students, but you will always be non-anonymous to the teaching staff, because that's the only way for us to meaningfully assess the kind of questions you are asking. So just wanted to do that. If you are uncomfortable with if you want to ask a question which is anonymous to us also, I don't have any easy suggestion. Perhaps discuss with me in that case. But I've struggled with this notion quite a bit. So I think a reasonable thing is you can ask questions anonymous to your classmates, but not anonymous to teaching staff. And then the final is extra credit. Teaching eval, we'll have a couple of them, one during the quarter, one at the end, add up to 1%. This is actually totally extra, so beyond the 100%. So that's the extra credit part. Let me just do one more slide and then we'll take a break, and during that time you can also ask questions. Okay, so the way I do grading here is the following. For every individual problem set or assignment or quiz or final, what we do is we take your raw base score, excluding any extra credit. Sometimes I offer extra credit problems, so we kind of exclude them. And then what we do is kind of this algorithm which is there, which is basically what it is doing is the following. It basically says the following. If the median is below 80% of the score, of the maximum possible, then I'm going to scale the scores so that the median becomes 80% and the highest score becomes the top score. Okay, so let's say the quiz was out of 100, and let's say the median came out to be 75, and let's say the highest was 90. So then I will scale it so that 90 becomes 100 and 75 becomes 80. Okay, and it's a linear scale. And if you think about it, what happens as a result is low scores get a big bump up, right? It's like a tail which kind of moves up very rapidly. So we do that for every individual assignment, and of course, if the median was already above 80, we do nothing, we don't lower it. And also, let's see, there's something else. So and then we add back the extra credits right after the normalization, and then for the overall course, the grading will follow as follows. Excuse me. 90 plus will be some sort of A minus, A, or A plus. 80 plus would be some sort of B, 70 plus would be some sort of D, 60 plus would be some sort of, 70 plus some sort of C, and 60 plus some sort of D, and below 60 is a fail. This if you think about it, at the median point, you are getting a B, which is actually more lenient than what the university's grading interpretation is, which is C is average. Okay, so so at average, or for a large class, average and median are often very close. So you're actually getting a, I think, I don't believe in like unnecessary filtering on the state. So that's a predictable grading schema. You might think that below 60 is harsh in terms of being failed, but do remember what this normalization is doing is it really, like, if you get a 0, so, let's say you didn't even attend the exam, right? I mean, I'll still keep it at a 0 in that case. But let's say you blew the exam, you just got 5 points, right? It booms up because of this grading formula. Okay, so everyone with bad scores, you kind of end up being pretty high. So I do stick with this less than 60 is fail. Okay, so let's take a, well, I guess this slide is basically saying, don't focus on grades too much, focus on learning. I think ECE and CS are very fun disciplines. So don't focus on that. Okay, I'll stop at this point for a little break. But if any of you have questions, shoot. Let's see. How long? Let's see. Are there midterms? Let me start. Is the quiz unlimited time? No, it is going to be either 30-minute or 45-minute. Okay, it's time enforced. It's synchronous. Other than the fact that we'll have 2 variants of it, right, for the 2 different time slots. Are there midterms? No. Are the quizzes supposed to be substitute for midterms? I don't know. I mean, they are more than your 10-15-minute quiz, so you can, if you want to think of them, you can think of them as like smaller midterms, okay, shorter midterms. For the quizzes, will we have to be on the Zoom meeting? No, you just log into Gradescope and just do it. I don't care, but it's probably useful to be on Zoom so that you can ask me questions at the time. All quizzes and exams will be take home. Yeah, everything is take home, right? I mean, everything is take home. It's open book. You can consult anything, but you cannot consult anyone or any service. So that's the honor code out here, right? So you cannot consult your fellow students. You cannot consult anyone else, prior students, external students. You cannot make use of any service. I know there are some services now which take exams for you or do homeworks for you. Remember, they come back to us, actually, some of them. That they will all be honor code violation. I'll talk about it later, but essentially it should be your own work, but you can consult textbook, you can consult class notes, you may not consult prior year solutions and all. How many quizzes will be there? 2 to 3. Will you drop the lowest quiz? No, because it's too few. I will not be dropping anything, I guess. Okay, anyone else with questions? Otherwise, let's do a 5-minute break and then we resume. Okay, I'm back. The interesting question from Jonah. So for Tesla self-driving, how do the ultrasonic sensors not interfere with the Teslas passing by? So great question. Anyone? What do you think might be happening there? So I think his question is the following, right? I mean, the way ultrasound sensors work is they send out an ultrasound waveform, it bounces off from nearby objects, and then you receive it, except if there's another Tesla nearby, or actually for that matter, any modern car, then your ultrasound signal could be picked up by their ultrasound receiver. So if you were designing this, how would you avoid this? So think of it like the problem of if you are in a crowded room, trying to talk. Multiple people are there, they're all trying to talk. So what do we do? Like, how do we deal with that issue of like not talking over each other? Anyone wants to take a stab at this?
Could you assume like a unique frequency for each ultrasonic sensor and then basically just use that as like a key?
Yeah, I mean that's a great suggestion. That's a great suggestion. It will work for radios very well. Unfortunately, not for ultrasound, because ultrasound transducers tend to be at very specific frequencies. You could, but it's not. It requires too much messiness at the hardware level. But you could do the same thing in terms of timing, right? I mean, you can have your ultrasound waveform carry some sort of a pattern which is unique to you, right? So it's like it's not simply like the frequency of the timing signal that you are doing, right? I mean, let's say you are sending 1010, maybe the pattern of 10 or the rapidity of 10, those things you can change. So that's one. The other part is these are short bursts, right? You send it out, comes back, so you do it with some random time gap, so you randomize it away. Okay, so this is how in radios also we kind of do things, right? We send something out after a random, if it fails, after a random delay, again do it. And this is electronics. You can still do it much more rapidly than what the cars are doing. So between a combination of these things, right, changing your signaling, changing the timing, you can pull it off. But great question. Yeah, so not different ultrasound frequencies, like as I commented, that is harder to pull off just because of the nature of these ultrasound transducers, but something akin to that. Okay, any questions on the grading part before I move on? Let's see. Okay. So yeah, okay. So one other thing that I wanted to cover is this. Late submissions. I realized that happens. Maybe sometimes it's like too many courses have their dates at the same time and all. So what I do is I give you a budget of late days. You are responsible for tracking them. At the end, I will just count how many late days you used, and if you exceeded, then we'll penalize you accordingly. Okay, so there is no like running place where you can go and check how many late days you have used. It's your responsibility. You can use them towards problem sets and design assignments. You cannot use them towards quizzes and not for the take-home final exam. I will give sufficient number of days for take-home final exam so that you can adjust things within that window. It's mostly because I have to grade. No more than 2 late days can be used towards any single submission. So essentially what it means is that if you have insufficient late days or exceed 2 late days, then your score goes down. Late days are used in chunks of 24 hours. So if you are late by even a second, that means you have used up 24 hours. Okay. When you are submitting, it's extremely important that you budget for the fact that there are like don't attempt to time Gradescope too finely. Okay, at the very critical juncture, your internet connection may be slow or whatever, right? I would strongly recommend upload preliminary version so that there is something sitting up there. We will also ask you to assign pages within Gradescope to your assignment in some cases, but that step you can do after submission. You still have to do it. If you don't do it, you'll get penalized, but that step Gradescope lets you do after submission. Gradescope also lets you select any of the previously submitted versions also. Let's say you submitted a version, then you decided, oh, I'm going to upload again, but now you want to switch back to an older version. In Gradescope, you can do that. So just familiarize yourself with these things so that you are not caught by surprise. All activities will be open book with no collaboration permitted with a person, service, company, etc. I will, in some cases, give personalized, randomized problems sets. Last time I had attempted that, mixed success. So depends. Design assignments will make extensive use of software tools. You will be submitting the design files. The tool we are using is this thing called Logisim, but they will be graded using the Gradescope auto grader. Problem sets, like I mentioned earlier, we may require some of the answers to be submitted as a structured text file, so that again they will be auto graded. Quizzes would be via Gradescope, and with a second offering. I still have to kind of decide on its precise logistics there. Last time what I had done, because last year spring was the very first quarter, the pandemic era, I had done that like one quiz at the end of the class and the other quiz at early morning hours, like 7 a.m. or something, so to minimize collisions. Cheating and plagiarism, you all know what it is, but university has kindly provided all these URLs where you can, but essentially, like I said, you shall not consult any person in all. And by the way, one thing I would also say, open book means open notes, open textbook. It does not mean going around identifying on the website or Chegg or these kind of websites and all solutions from previous years. That's cheating. Using other people's ideas, and also if you contribute, like oftentimes I have these cases we catch, and then one student says, but I only provided help and therefore I'm not at fault. That is not the case. The other thing I would say is, if you are showing your solution to someone over Zoom, be prepared that that other person can do a screen capture. And at that point, you have unwittingly contributed to it. I have had several cases like that. In all these cases, I just report to the university and you'll have to kind of deal with that. I would basically say that if you are, firstly, one suggestion I have is that ask these questions on Piazza in the open, right? Because so that everything is in the clear. Do not show your solution. Do not show your design, because if the screen capture is done, the other person can replicate your design. And at that point, like I said, you have violated the things. It's okay to discuss what a question means, what approach may in general be. It is not okay to share specifics. So yeah, hopefully this stuff is mostly self-evident. I mean, really. Okay. So I talked earlier that how design tools and design languages and all are a key part of how we do digital design. And so this is where I had to make a choice whether to expose you to very complicated but industrial strength tools versus simpler tools which get the concept out but are not one which the industry uses. I erred on the side of the latter because most of you will not be headed into professional digital hardware design. But in the follow-on lab course, 116L, you do encounter Verilog, which is a programming language, although again, not in a very significant manner. And then in later courses, you have it. Logisim is something which gets the concepts across, and it actually has features in it so that you can export and import designs in hardware description languages, but it's primarily an educational tool, but it's a pretty good one. We will specifically use the version which is on Piazza under the resources section, right? So if you go on Piazza, right, that's the version I want you to use, and nothing else. Okay, so go to our Piazza website. So firstly, this resources tab, this one is kind of one of the most important things, because that's where everything is. This is like the course website for all practical purposes. If you go down out here, there is this digital design tools, and this Logisim Evolution recommended version is what you need to use. If you are on a Mac, read this document, Java on Mac OS X, because this tool and another tool we'll use called FISM, they both use Java. Java on OS X has a little bit of finickiness to it, the interaction between the OS and Java. So read this instruction. Akash will probably post a video in any case. Do bear in mind that unfortunately, it's not possible for us to test every possible combination that may exist between operating systems and all. I personally have the latest OS X, Big Sur. You may have an older version, Catalina or whatever, Mojave or whatnot, right? I mean, they all have some differences. Windows, Star confirms that he had a relatively easy time installing it, but again, Windows has multiple versions. So when you contact us about these kind of issues, it would be very important that you tell us what operating system you are using, right? So that we can sort of guide you a little bit. We have tested this. I mean, this tool I have used last year's course also. So these things work. There's no fundamental problem, but again, there are uniqueness in every computing setup, and you'll just have to sort of bear with us. One of your tasks this week is indeed to make sure that your installation is up and running. Okay. It also works under Linux. In case you're a fan of that, you do need to have Java 9 or newer. Unfortunately, on Mac, Java 16, which is the latest Java, does not work with these tools. So, and again, if you go on the same website, the Piazza, you would also see that I have some links like this lab videos and all. So there's plenty of sort of resources that sort of are provided you in case you run into trouble. So that's the main tool that we'll be using. So download and play with it before discussion section. Course outline. So these are the topics we are going to cover. There is a set of topics, and at the very end, there are some additional topics. We're probably not going to get into it. So these, I'm not sure, but all the initial stuff we will certainly cover. So initially, we start with sort of dealing with low-level representation of digital systems, digital information. Then we move into sort of more building blocks that make digital systems, and then finally we go into system level issues. I guess time falls under it. My animation is messed up a little bit. So these are a set of topics that correspond to the textbook in terms of chapters, as I had in one of the earlier slides. So there is reasonable synchrony, although they are not necessarily in order, same order as a textbook. Okay, so list of important things to do: download and install Logisim, read the documentation just to familiarize, sign up on Piazza if you haven't done so, verify you are able to log in onto Gradescope. You should see this course there. It might appear as CSM51A. I think in some places referred by that, in some places by M16. Download and look through the slides. Basically, okay, so, it might be useful for you to just take notes on the slides as I speak, but you always have access to the video. So yeah, there. I will also post a version of the slide with the annotations on it, so you will have access to it, although video is probably more convenient. If you have the textbook, you might find it useful to read the corresponding sections prior to each class. And also, finally, we do cover this course has a lot of material. Essentially, just think of it this way: it's 40 hours of lecture, which is pretty much the same what happens in a semester course, right? 13-14 weeks, 3 hours per week, so similar number of lectures, except there it is spread out over 14 weeks, right? Here it is over 10 weeks, same material, same amount of material. So very easy to fall behind. And so we are there to help you, but of course, there's only so much we can do. So try not to fall behind, try to stay. I know it's an intense, it can be intense at times. So yeah, week 1 tasks, again, that's just something. Any questions now before I start on the next lecture module? Okay, if not, let's move on. Okay, So the first thing we are going to talk about is how do we represent information digitally? Okay, so previously we saw that, loosely speaking, as several of you kind of said, it's about expressing information in discrete set of discrete values. But what we will see is that there are many different ways you can do even that part, right? There is not a single unique or even optimum way of representing information in a digital manner. For it's a function of what your application is, what you want to do with that information, and also we're going to look at some of those issues. Okay, so it roughly corresponds to chapter 1. Okay, so let's go to it. So digital systems have discretized inputs and outputs. We saw that as the definition of digital system, right? So system as input output, digital, and it processes that information. Very importantly, generally, a system doesn't have to be electronic. It could be chemical, it could be mechanical, it could be pneumatic, optical, whatnot. And in fact, computers come in all these shapes, in all these varieties. So even though the most dominant form of digital systems are based using silicon-based electronics, that's just one type of digital system that exists. And in fact, past has been different, and future will in all likelihood be different, because I'm sure you may have heard these things like Moore's law is dying, or silicon chips are reaching their end of life and all. Now, the notion of what a system is very general. Obviously, a car is a system, right? It takes our whatever hand motion and feet motion as inputs, and then output is, well, it drives on the road. So system concept is pretty general, but and you'll see lots of places, right? Our phones, human input, and sound and stuff like that as output. Wi-Fi router gets wireless packets over Ethernet, and then again generates packets over Ethernet and wireless. A radar sends out radio waves, looks at the bounced signal, and processes them and all. So these are, I mean, almost anything which has some utility will probably have some input and output, right? I mean, if it has only input and no output, then it's a black hole. And if it is only output and no input, then it's probably just generating some simple pattern. A digital system takes inputs and output which are discrete valued, and it processes them in a digital manner. So by discrete, we mean they come from a finite set, like open close, 0 through 9 digits, or A through Z letters, and whatnot, right? I mean, any discrete set. And likewise, the output would be the same way. Now, the question is, must it be electrical? And as I mentioned earlier, it can be electrical, but even if it is electrical, it could be many different ways. So anyone, could you tell me in what ways can we represent digital values electrically? Like what electrical quantity or quantities can you use to represent a set of discrete values?
You have a voltage threshold.
Yeah, so voltages is one. Can you think that's the most common one, surely? What about some other things? Transistors you can use to build the digital systems, but not to represent the values, right? But the state of the transistor can represent zeros and ones, for example, right? But what about some other things, other quantities, other electrical quantities also, right? I mean, besides voltage. So can you think of using something else? You can, for example, use current, right? If the current is flowing or not flowing, or whatever, two different quantities of current. So exactly as you are doing for voltages, you can do it with current. You can represent zeros and ones with values of capacitance or values of charge. Any number of electrical quantities can be used to represent binary or even multi-valued discrete thing, right? I mean, I can have 10 different voltage levels and represent my digits 0 to 9. Okay, so I can do things electrically. But I can also do things in other ways. So actually, let's see. Let's say, can you do it chemically? What would you use to represent discrete values if you were to do things chemically? Actually, firstly, can you think of a computer which operates chemically, or which does computation chemically?
Isn't the clock, or sorry, atom clock? I'm not sure.
Atomic clock. It's not chemical, but yeah, it is a physical phenomenon, but it doesn't do any computation. It just oscillates. But there are quantum computers which do computing using the quantum states. Okay, so probably will not call them chemical still. They're more physics based than chemical. But our brain is, the firing of the neurons. You may have read in biology classes, right? As the chemical concentration inside the cell changes, it results in an electrical spike firing, and also it's a electrochemical phenomenon which goes on. That's how our brain works. Neurons, our thoughts and memories and all, right? This is an electrochemical computer. So that's a figure out why my pen is not working here. Okay, so brain is electrochemical. Okay. Generally speaking, you can use chemical concentrations, right? Discrete values, just like we are using voltages, right? Not really any different, really. So that's chemical. You can also do computation using other kind of phenomena like air pressure. Maybe I can do it using that, right? I mean, because again, I can represent values, right? Different amounts of pressure, and then create some sort of a pneumatic computer doing it. We do it. Optical, right? So optical can be done by intensity of light or color of light, right? Those kind of things I can represent, like the frequency or wavelength of light, right? I can do it that way, or presence or absence of light. So there are a variety of ways I can approach. One can approach these things. Probably one of the first electrical computer was really Alan Turing's bomb, which was designed to break the German cipher in 1940s. Kind of this movie Imitation Game is really the story about that. And if you ever visit Bletchley Park near halfway between London and Oxford, you would in UK you will find this original machine, which every hour or 2 hours they actually run. That's pretty cool. I've been there. It's a lot of fun. So all these little dials you see, and all these are essentially motors. And in the movie, kind of you see that how, like, by modern days, obviously it's a pretty slow computer. Okay. But Turing, obviously, in part because of this work, but in part also, he kind of came up with really what people say is the theoretical, what is the theoretical foundation of computing, right? Which is what does computing mean? What is computable, right? All those kind of very fundamental questions that he started on. So that's why this Turing Award, which is like the Nobel Prize in computing. Computing meets math, I guess, in that space. And then this Turing test. Anyone knows what Turing test is? Have you heard of it? Like, why is that famous? So Turing test goes to, I mean, many of you are in computer science. I'm sure you aspire to learn about AI and all. Turing test is the litmus test, or what Turing proposed as the litmus test for intelligence. And essentially, he said one way we can claim that we have achieved success is the following: that I'm interacting with two entities, one of which is a computer and one of which is a human, and kind of I'm hidden from them. Like, I submit a question and this entity answers, and by just examining this, like, I give this box inside which would be a computer or a human, I give it let's say an oral or written question, or and then it answers back. And by examining that, can I tell whether it is a human or a computer, right? So that can I distinguish between the two? And that is referred to as a Turing test, that we would claim that we have designed a computer which has human-like intelligence when it is able to pass that indistinguishability test. Okay, so that's what Turing test is very famous for. There are variants of it and all, and I'm kind of hand-waving my way around it. But this idea of like creating a black box with which you interact for purposes of intelligence or other such thing is a very common thing which is done in computing. So anyway, if you aspire to be an AI and all, Turing test is kind of ground zero of that. The movie obviously talks about, is more focused on this specialized computer which Turing designed to to break into cipher. Thing I also wanted to point out is I kind of see nowadays a trend that students who are doing machine learning and computing and all kind of forget that forever in history, hardware and software have gone. And I mean, here we have someone who literally created computer science theory. On the other hand, he was building these super cool, first of a kind computers. Now, Turing was not the first one to create a computer. The very first programmable computer was a mechanical computer, and it was done by a person called Charles Babbage. And actually, a very interesting thing about it. So, you know, in academics, there is a lot of people are fond of like they create their academic lineage. So the kind of the idea is like Akash is my PhD student, right? So I would be considered Akash's academic parent. Okay, so people draw this lineage. So someone I know from the group I graduated at Berkeley kind of created the lineage, and it seems like Babbage is in my ancestry, academic ancestry. So anyway, little interesting tidbit. I don't know whether it's true or not, but at least that's what that guy found. What Babbage did was he created this mechanical computer. Kind of the idea was that it had gears, and the gears had teeth, and so they represent values, and then the gears enmesh with each other, and then they move, and then they compute. So you could set this this computer had memory where you write a program, it would run, produce the result. In this particular case, it would solve certain kind of equations. In late 1980s, with money from some rich person, people UK kind of replicated this machine at 8,000 parts, roughly half in the computing part and half in the control part, the one which has a program, weighs 5 tons, measures 7 feet high, 11 feet long, 18 inches deep, essentially like a big supercomputer. 2 copies, one of which is in the London Science Museum, which if you ever get a chance, you absolutely must visit because it has some of the coolest things out of human history present there, besides this computer. But the other copy is in the private collection of Nathan Myhrvold, who actually, again, interesting tidbit. So he was a CTO of Microsoft. He is a Los Angelian. Those of you are from Los Angeles, he went to this famous school called Merman, which is for whiz kids, and he is now very much into fancy cooking, and he has a super cool book where on cooking, where he, as the dish is made, he kind of freezes the dish and cuts it open and shows you the inner state, and then kind of time-lapse version of it. It's a pretty cool, cool stuff that he has done. So he's a pretty cool person. But anyway, the second copy is with him. There's a close-up out here. Now, as I was researching about this some time ago, I kind of found a lot of things. So there's a very nice sort of YouTube album which goes into how the Charles Babbage engine works, right? How's the program? How's the thing? What I found very, one other thing, the first programmer, the person who programmed this thing was women. Okay, I mean, nowadays we have a lot of concerns, right? Naturally, that computing doesn't attract as many female students and whatnot, and it's oftentimes like hacking and all is viewed as like a guy's thing. Just remember, the first programmer was a female, Ada Lovelace, and there is programming language called Ada, which is named after her. And so super cool personality. If you read about her life history and all, like in that time, right? I mean, when women were treated even far worse than modern age, and yet sort of, so she was essentially Babbage's collaborator and was the math person behind that, doing things. So okay, so that's Ada Lovelace. Now, another question which, so first computer was mechanical, and I guess in 1940s, electromechanical stuff began to come into play, 1930s and 40s, okay. And then gradually, then we had silicon transistors and so on and so forth. One question which comes up is the following. When we go from analog to digital, remember I talked about earlier on that we take analog values and through A to D converter, we kind of convert it into a digital signal, we discretize it. Do we lose the original information, right? I mean, our music is all digital now, right? These are just bits on your MP3s and such files. So what's going on under the hood is that we are taking this analog waveform, right? The one which our microphones pick up, and then we digitize it, right? And we digitize it by discretizing it in both value, right? I mean, we basically create some thresholds of voltages, let's say, and then give them different discrete values. And we also sample in time, right? Each vertical line out here is representing an instant in time when I actually sample the value. So, so maybe I will say I'm sampling it every 1 millisecond. You might often, for audio files, you will see things like it is sampled at 44 kilosamples, right? So that means that it is sampled at 44 kilohertz, which is pretty, for audio signals, is a pretty good thing. And you can, as you might imagine, if I sample more, you would intuitively think that I have a better replica. My discretized signal is a better replica of the analog one. So the question I have is the following. This process that we are doing, do you think we are losing information? Right? I mean, so clearly for my digital signal to be compact, I would not want to sample too frequently, and I will not want to have too many levels, right? Both how many levels do I use to represent the signal and how often I sample, both that's what controls the size of digital information that I'll have. I guess my question is the following. What do you think? Is it the case that I will always lose information if I were to digitize? And if not, under what conditions do you think we might not? So it's an advanced concept. So firstly, intuitively looking at this, you'll say lossiness will depend upon how many levels I have, how often I sample. But there is actually a pretty cool, very profound result, coming from roughly around the same time that Turing was doing his work. Those 1930s were like golden era of computing. Also a guy called Gödel who created some pretty cool stuff. Shannon is like the father of much of information science, right? So Shannon and Nyquist were at this famous lab called Bell Labs, which is what AT&T Bell Labs. Okay, so there is some pretty cool work there. Okay, so intuitively, it would seem that if I'm sampling like this, I will always lose information, right? Because what is happening is that if I have original signal like this, I decide to sample at these points, and let's for a moment forget about discrete values. Just because I have these discrete instants of time, so all I have is the values at these points, right? And then of course, then I convert them into discrete values. So it would seem like in the middle, I really don't know what is happening. I can fit this signal to those samples, but so can I fit this signal. How do I know which one is right? I mean, this or this. So of course, stated this way, it's clear that there is no single answer. But what these guys, Shannon and Nyquist, did was a very cool result, which basically said that under some assumptions, in particular, if so there is a concept of bandwidth that those of you who are in electrical engineering will see plenty of. So you can think of like a signal is made up of many periodic waveforms. Okay, in math you have done Fourier transforms. I'm pretty sure many of you may have seen it even in your high school. So I can take a signal and break it up into a bunch of sinusoids of different frequencies. So bandwidth refers to, loosely speaking, what is the highest such frequency in my signal, right? In my, let's say, speech waveform. And what Shannon and Nyquist showed was that if I sample at more than twice the rate, so let's say the highest frequency in my signal was 100 hertz, then Shannon and Nyquist showed that if I sample at 200 hertz, then I can perfectly recover the original signal back just from these samples. And if you think about it, it's pretty mind-boggling, right? I mean, we sort of, from a finite number of samples, I'm still able to recover the original sort of continuous time waveform. In fact, things have become even cooler. So in around 15 years ago or so, there is another body of work emerged, included by folks at Caltech at UCLA. So Professor Terence Tao, who's the field medal winner here at UCLA, they developed this area called compressive sensing, which shows that you can go oftentimes for real signals, like real world signals, right? Real sounds, real images, things like that, videos, right? Sensor data, you can go another 10x or so lower often, okay? That these real world signals have certain properties that I can sample even lower than what Shannon Nyquist said and still be able to perfectly recover or perfectly recover almost all the time. That's precisely what the result was. So this is an advanced concept. I don't expect to know it, but just wanted to mention that there's some pretty cool stuff right on some of these questions, and they play into, again, kind of these things are also connected all the way back into some of the more fashionable stuff you read about in machine learning and things like that, right? I mean, these things kind of feed into that. Okay, so I'm at the end of the time, so I'm going to stop out here. So what we saw thus far is that we can represent signals in a variety of different ways, not necessarily electrical, that converting continuous value, continuous time signal into discrete value, discrete time signal. Discrete value does result in loss of information, right? Because, but discrete time, there are these results that we saw, which suggest that I can still recover things, right? So so that's what happens out here. So I'm going to stop out here. We're going to pick things up. Let's see if there are pick things up on Wednesday, but let's see questions out here. Light, brain, current, yes, all right. Radiation detector, yeah, radiation can be okay, yeah. So sample 2 times frequency for Nyquist sampling rate. So Alethea, yeah, you're absolutely right on. What exactly does the bandwidth mean? So again, just very intuitively, you can say, like, if let's say I have radiation, right? It will have different components of different wavelength in it, right? Light, like if you're, let's say you're looking some light, right? It would have a lowest frequency and it will have a highest frequency or whatever, highest wavelength and lowest wavelength corresponding to different colors. Bandwidth is the max minus min. Same thing is true for sound, right? I mean, I may have, let's say, from C in one octave to C in the next octave, that gap, and let's say that is the lowest note and the highest note, that gap would be the bandwidth. So that's a way to think about it. It's a bit of a, yeah, it's you'll see in, if you're a ECE student, you will certainly see it in some courses, but just a pretty cool concept, but a little bit abstract also at the same time. Okay, any other question, anyone, before we hang up for the day? It's in ECE 102, absolutely. So if you're doing 102 or already done it, then you have seen this stuff. Okay, anyone else with comments or questions? If not, so I'm going to hang up. So we will have office hours starting from tomorrow. So tomorrow is, I think, my turn, 6 to 7. So come by, even if you have no questions and all, just come by, say hello. I'd love to get to know some of you. I think one of the disadvantage of this online format is that the whole quarter will go by and I'll never meet any one of you. So come by. Okay. Otherwise, we'll see you on Wednesday.